All right, ladies and gentlemen, welcome back. In terms of announcements, I don't think there are any. Yes, of course, your term exam is on Wednesday. There was a question last class with regards to which sections were on it. And while part of Chapter 16 was covered in term exam 1, the second half of Chapter 16 is going to be in term exam 2, but the second half of Chapter 16 actually is nothing more than applying the first half to things like titration curves and the like. So it's pretty much all of that is testable material. So Chapter 16, 17, 18, 12, and 14, all of the information you need should be online. One request just to put out there, the answer key to problem set 5, I think it is. Yes, the answer key to problem set 5. I literally created that over the last week and typed it all in. So there may be an error or two on there. If you could bring that to my attention, that would be great so that I can go in and correct it because I'm typing these things in. So again, if you do find anything different than yours, please just send me an email. So. With regards to the question that was posted under the chat, is the term exam going to have a lot of short answer questions? The answer is it's going to be, as before, a mixture of short answer and a mixture of calculation. Might be one or two fewer questions than before, but it is, in order to answer the short answer questions, you need to know the material. Paragraphs upon paragraphs of text are not the answer that is expected. It should be able to be answered in one or two sentences at most, and that's the level of understanding I expect you to be at. You read the question, you answer it in one or two sentences, and you move on to the next question. If you're giving me paragraphs of texts, you're probably missing the answer. Does that answer your question, Mark? All right, so last day, we started looking at thermodynamics, and although it isn't testable, I'm going to continue with this material. We initially started this chapter looking at entropy, introducing the concept of entropy, and looking at it from Boltzmann's view perspective and Clausius' perspective, which I kind of blended together into this concept of microstates. The idea of microstates looks at very little energy and very few particles, and with it we're able to generalize to macroscopic systems where we have many particles with lots of energy. And the simple point that we came out of there is that with more available energy, if I can get back to it, as the energy level increases, the number of ways of distributing the energy amongst the available particles increases, and when the energy spacing decreases, you get more ways of distributing the energy. The one thing that we did do that looked at taking this to a macroscopic perspective was this figure right here, which looked at how big of a pressure differential is there in this flask. Once I open the valve, the pressure equalizes, yes, but how equal is equal? And the answer as presented here is you are very equal. If 10,000 gaseous particles has a very narrow distribution at 0.5, 10 to the 23, 1 mole of gas, or even a small flask, small balloon, with 10 to the 21 or 10 to the 22 gas molecules is going to be nothing but a straight line at exactly an occupancy of 0.5. It will be a delta function. So we did one extrapolation from a few particles, 2, 3, 4, 10, whatever, up to macroscopic quantities. But in general, the realm of that is statistical mechanics, and we're just going to, we looked at microstates, now we're going to look at it from a macroscopic perspective and avoid the math that's in the middle. If it's something that interests you, phys chem all the way, or certain aspects of engineering actually too. So we ended off talking about this last day. When we want to apply it to macroscopic systems, there's a couple of generalizations that we can do, and that is here. When I want to talk about the entropy of a system, before I go into this, did you have system, surroundings, and universe explained to you in detail in Chem 100? Was that something that was gone over by whoever taught Chem 100 to you? The difference between systems, surroundings, and universe. No, and I think so. Just very briefly, system is the reaction you're looking at. It could be the beaker on the bench or the reactor flask or whatever. That is your system. Your surroundings are what can either provide energy or material to the system. So in a chemistry context, if a beaker's sitting on a bench, the room has enough to be the surroundings, and the universe is simply the system plus surroundings. From a chemistry perspective, like I said, a room or a building where a reaction occurs is perfectly fine, where the flask that it's occurring in is the system and the building is the surroundings. If you have different disciplines, say you're an engineer, you're designing a bridge or a building, the bridge or the building is the system, the surroundings are whatever can affect it. The river, the atmosphere, the weather, the earth, the tectonic plates, that type of idea, and you need to account for that in terms of your surroundings. If you're a climatologist, very likely your entire globe is your system, and the surroundings are what can contribute energy to it. That is the solar system, and we go from there. Anyway, so we'll talk more about that in a little bit, but I just wanted to remind you or bring you up to speed on this idea of system, surroundings, and universe. In the context here, we're looking at the system. What happens within the molecules? The system entropy increases when we add energy. So adding heat can increase the temperature. Increasing the temperature means that there's more energy levels available, or it can result in phase transitions, solid to liquid, liquid to gas. That also makes more energy levels available. We'll talk about that in just a bit. When the system does work, it expands. Expanding the volume of the system makes more energy levels available. We'll talk about that again next slide. And when the number of entities increases, so you go from one big molecule to a bunch of smaller molecules, a reaction is occurring that does that. It's going to be an increase in the entropy of the system. Or as we increase the complexity of the entity, we also see an increase in the entropy of that entity. So to look at increasing the temperature means that there's just more energy available, and you can see here the energy initially is fairly low, such that you only have the ability to populate 4 energy levels, and at the end of this you have a higher temperature and you have 8 possible energy levels, enough energy to populate up to the 8th energy level. So how you distribute it amongst those energy levels now increases. When you do work doesn't change the amount of available energy. The amount of available energy is fixed, but, and this is beyond the scope of this course, the energy level spacing decreases. So even though as I increase the volume from something that's really, really small on the left-hand side to something that's really, really big on the right, you end up seeing more energy levels in that available space. And of course, same amount of energy, but with more energy levels means you have a greater number of ways of distributing the energy. If you increase the number of molecular entities, you have one thing that kind of moves through space versus a whole bunch of small particles that can move anywhere, means that there is an increase in entropy. The randomness or the freedom of the smaller entities is greater than one big thing moving through space. And with regards to phase transitions, there are 3 modes in which energy is stored within molecules. Energy can be stored in translation, that is, molecules moving through space. It can be stored in the rotation of molecules, and it can be stored in vibration, either as bends or stretches, as presented there. When you have a solid, all of the atoms are fixed in space. And if you think back to the picture of liquid, well, ice, not liquid water, but ice, the hydrogen bonds held the water molecules in exact locations. They were hydrogen bonded and they were locked in position. The only thing that those molecules in a solid could do is vibrate a little bit in their fixed lattice point on the solid. So in a solid, all you really have access to is vibrational energy levels. When you go from a solid to a liquid, thinking again about water, you break one or two of those hydrogen bonds and the molecule can now move a little bit more, has the ability to a little bit rotate and move past its neighbors. It can now translate a little bit and it can rotate a little bit. So in a liquid, you have accessible some translational energy modes and some rotational energy modes, although they're hindered. Going into the gas phase means that the individual molecules are completely free and independent of each other. Free and independent means that this water molecule and this water molecule they can translate, they can rotate themselves, they can do whatever they want. So they have complete freedom in the gas phase. Solid, it's only vibration. Liquid, you have vibration still and a little bit of rotation and translation. And in the gas phase, complete freedom for vibration, rotation, and translation. That can be illustrated down here when we look at the entropy at 298 we'll just look at liquid water. In the solid, it's 45. In the liquid, it's 69 or 70, for example. So that's an increase, 45, 25 kilojoule or joules per mole Kelvin. But going from a liquid to a gas, it's going from 70 to about 190. There's a significant increase going from the liquid to the gas and a small increase going from the solid to the liquid. And that is due specifically to the much greater translational and rotational freedom that is afforded by the gas phase. This table actually was supposed to look at increasing the molecular complexity, and we go from water, which has 3 atoms, to methanol, which has 6 atoms, to ethanol, which has a few more, 3 more, 9. And you see whether you look at the solid, the liquid, or the gas, as you increase the complexity, the entropy of the entity will increase. So that illustrates those 3 points. When you add energy, when the system does work, or when you increase the number of molecular entities. What I'm going to do now is I'm going to go back to Boltzmann's definition of entropy. S is equal to KB ln W. And that leads to the third law of thermodynamics. The third law of thermodynamics simply says that the entropy of a perfectly crystalline solid at 0 Kelvin is 0. That is, when there is no energy available, there is only one way of distributing the energy, there's lack of energy, into the particles, and that means all the particles are at their lowest energy state. So natural log of 1 is, of course, 0. So at 0 Kelvin, 0 energy available, only the lowest energy state is populated, and that 1, natural log of 1, is 0. As we increase the temperature, we add energy, more states become available, and ways of distributing that energy amongst particles increases, and so you see an increase in entropy. This is the absolute entropy of water, but it can be applied to any molecular entity. So one could create a figure for methanol, for aluminum, for pick something, and it's possible to do. But we're going to look at it for water. At 0 Kelvin, there is 0 system entropy. Okay? And so you have perfectly crystalline solid, 0, ice, and it sits there with an entropy of 0. As we increase the temperature, the amount of energy, of course, goes up. We can start populating some of those vibrational energy levels, but it's not enough to, of course, melt the solid. So there is some entropy as you increase the heating. You're heating the solid until you get to the point where you have fusion or melting of the solid. Now, melting of the solid allows some rotational and translational energy, modes available. So you see a slight increase in the entropy due to fusion or melting. Then you can heat the liquid up, and there is a significantly greater increase in entropy due to vaporization. Vaporization breaks all the intermolecular bonds, so while they were just moving a little bit in the liquid phase, they are now free to do whatever they want in the gas phase. And so the entropy of vaporization is much greater than the entropy of fusion. And yes, you have completely independent water molecules that are free to do whatever they want at that point. We can tabulate this thermodynamic data. Now, in Chem 100, when you did thermochemistry, you would have looked specifically at reaction enthalpy, and you would have been able to use this column and calculated the reaction enthalpy for whatever reaction you're looking at. Here, we also tabulate the entropy of these entities, and in tabulating the entropy, we can actually go through and calculate the entropy of a chemical reaction in the exact same manner that we do reaction enthalpy. Now, realize that the units are slightly different, joules per mole Kelvin, etc. Excuse me. But it's just tabulated data. These have been experimentally measured and tabulated for use. The calculation of the reaction entropy is, as I said, calculated exactly the same as reaction enthalpy. Products minus reactants of the individual entropies multiplied by the stoichiometric coefficients. So we create or calculate the reaction entropy the same as we calculate the reaction enthalpy. We'll come back to this calculation in a little bit. Right now we're going to go back to this idea of needing to identify a spontaneity indicator. And this comes now from the second law of thermodynamics. So the second law of thermodynamics says that all spontaneous processes increase the entropy of the universe. So delta S universe for a spontaneous process is greater than or equal to 0. And this is where it's important that we worry about system, surroundings, and universe. The system is what we're focusing on the bench. The surroundings are whatever can feed material or energy into the system, so the room or the building. And the universe is the summation of system plus surroundings. The second law of thermodynamics defines a spontaneity indicator. Basically, it says that the universe entropy must increase for a spontaneous process. Must be greater than or equal to 0 for a spontaneous process to occur. Further question. Just looking at the chat, I don't know what question I missed there, but I hope if it didn't get answered, just let me know. My question for you is, what do you remember about state functions from Chem 100? What do you remember about state functions from Chem 100? Anything? Nope. It's not that they depend on the state of matter. Okay. No, it's in the textbook. A state function is anything that a state function is a property of an entity that is independent of how you get there. So this water bottle of course, contains liquid water. Oh, wait, love how it distorts the picture of me. That's a different story. The water bottle contains liquid water. I'll just get my head out of the way so it doesn't look so funny. And what ends up happening with the liquid water? Any property of the system that is independent, that I can tell, for example, it's clear and colorless, okay? It's got a density of 1 gram per milliliter. I can measure the heat capacity. I can measure the enthalpy of formation. All of those are state functions. It doesn't matter how I got this water. I could have reacted hydrogen and oxygen and collected the product. I could have taken the drywall. The drywall behind me in all the buildings is gypsum, calcium sulfate dihydrate. You take that, you heat it, and water comes off that you can then collect and purify. So there's many ways of getting liquid water. If it doesn't matter how you get it, it's a state function. So things like enthalpy of formation, entropy of formation, all of those are state functions. The work is not a state function, and heat are not state functions. The heat and work of a system are not. But universe entropy is the other one that is not a state function, which basically means that it doesn't always have to, it varies depending on how I go from reactants to products. We actually saw that at the beginning of this unit where I talked about iron rusting. I can change the conditions, I can change the environment, and I can reverse the process. That means that the entropy of, that means that, what does that mean? If I can change the conditions, it means I can create a process that becomes spontaneous. The entropy of the universe can't be a state function because of that. Sorry, wrong place. What we're going to do is just use our general understanding of chemical reactions, and we're going to determine the sign and magnitude of the entropy of the system, surroundings, and universe for each of the following reactions. And hopefully this will kind of illustrate what we're getting at. I'm actually going to jump over to the tablet to do these, and so just let me go over there and rewrite them. So just looking at the first two for now, we have got solid going to liquid. So just looking at the system, solid going to liquid, is that an increase in entropy or a decrease in entropy when I go from solid to liquid? Increase or decrease? That is an increase in entropy, right? So the system entropy is positive. Now, does this process occur? Does solid water convert to liquid water at minus 10 degrees Celsius? It does not. So this process isn't actually spontaneous. It doesn't actually occur at minus 10 degrees Celsius. So this universe entropy is negative because this doesn't actually occur. What this says about the surroundings is that it must be more negative for such that when you add system plus surroundings, you get an overall negative process. Let's look at the second one. Just looking at the system, gas going to liquid, is that an increase or a decrease in entropy? Gas going to a liquid, looking at the system. Right, gas to liquid is a decrease, so that means this is negative. But at 25 degrees Celsius, does gaseous water condense to liquid at 25 degrees Celsius? What's the standard state of H2O at 25 degrees Celsius? It's liquid. So that must mean that if I had gaseous water vapor, it's going to condense to a liquid. And it does. That's what we call clouds and rain. So this process actually occurs. And the threshold is considering 1 bar or 1 mole per liter. Can I get 1 bar of gaseous water at 25 degrees Celsius? No, I can't. So it will convert to the liquid. And that means that this is more positive in order to make this process actually occur. So look at the next two. Now, these two are just the reverse reactions of each other. We have solid water going to liquid and liquid going to solid at 0 degrees Celsius. If we look at the system solid to liquid, we actually already did. Solid to liquid is positive. And that must mean liquid to solid is negative. So there we have the system entropy for each of these two processes. Does this first reaction occur spontaneously? Does solid water go to liquid water at 0 degrees Celsius spontaneously? Yes or no? I got 2 no's and a yes. How about the second one? Does liquid water spontaneously go to solid water at 0 degrees Celsius? Yes. So if liquid goes to solid, why can't solid go to liquid at 0 degrees Celsius? It can. Benjamin's adamant that it can. And he's right, it can. It does. Both of these processes are spontaneous. If both of those processes are spontaneous, what do I put here that says that they can both be spontaneous at the same time, even though they're equal and opposite? Right. If I go back to this figure right here, or this process right here, what it says is that delta S universe for a spontaneous process is greater than or equal to 0. So if it's greater than or equal to 0, the only way that two opposite reactions can be spontaneous is if they are both equal to 0. What do we actually have occurring at 0 degrees Celsius? Anyone? Sorry, I need to go there. Is that not the freezing point? It is the freezing point, yes. But what we have is that delta S of the universe is equal to 0 when you have a system at equilibrium. And to finish off this table, this has to be equally negative and equally positive. What you have at 0 degrees Celsius is an equilibrium system. You have liquid going to solid, solid going to liquid. And delta S universe is equal to 0 for any system at equilibrium. Go ahead, Afrin.
I'm still a little confused how you can go go from a solid to liquid at 0 degrees if that's the freezing point? Because I don't see how it could turn into a liquid at that temperature.
So your question is, if it freezes at 0 degrees Celsius, how can it melt at 0 degrees Celsius? Realize that those two processes are equal and opposite. So if you have the reaction H2O solid is in equilibrium with H2O liquid, this is truly in equilibrium. The process going to the right, solid to liquid, we call fusion. The one going to the left is crystallization. And it literally just depends on what's happening. So if you take, for example, ice cubes and you put them into a drink at 0 degrees Celsius, you're going to get a little bit of heat coming in from, let me just go back over to here so you can see what's going on. Why didn't that work? That works. So if you take this ice cubes and you put them into a drink, okay, there's a little bit of heat coming in, and that heat from this environment, and that heat is slowly melting those ice cubes, and so you're going from solid to liquid. However, if you take that and you put it into, say, for example, a freezer, the energy is slowly bleeding away. So even though the temperature is 0 degrees Celsius, the heat flow is either going to, coming in, melt some of the ice, or going out, cause more of the liquid water to freeze. That is the equilibrium aspect of this process. Does that make sense, Afrin, Jada?
Yeah, that does make sense. Thank you.
All right, good deal. So now we looked at that. Here's one for you to work on. So I would like you to go through and realize that our criteria is 1 mole per liter or 1 bar pressure. Can you create 1 mole per liter solutions of what's presented here? I would like you to, I'm going to put you in breakout rooms and go through and determine the signs and relative magnitudes of system, surroundings, and universe entropy. You have 3 minutes starting now. So just work on it and you'll eventually get in the breakout rooms.
Hi, Roy.
How's it going?
Not bad. How are you?
Pretty good, Shmita. How's your weekend?
Just while everyone's
Yeah, go ahead.
in breakout rooms, I just wanted to double check that there won't be any class on Wednesday because of the exam, right?
That is correct.
Okay, someone in the chat is asking if
Yeah, I got that.
temperatures.
Good question. Let me just mess with people's minds. Do you see what I just did to the slide?
No, I might have missed it.
I added add SATP.
Oh.
So I will go and give. I will go. Was it Mark who asked that? Yeah, Mark. hard time. Said that right in the question. What time is it? Oh, they got another 30 seconds, so. So yeah, there is an exam on Wednesday, so you don't need to be around. You get a little bit of a break, I guess.
All right, sounds good.
How's your term going?
It's going all right. Getting into crunch time, I guess.
For everybody, everything's changing
Yeah.
here too, right? So labs are getting done. We got presentations to do. Panic, do you want to come to some of these presentations on your own time? Is this of interest to you?
It depends on how it would work with my class schedule, but I wouldn't mind seeing what they're like.
You will. I'll send you out the thing, the thing. So if you find something that's interesting, yeah, and if you can make it, great. Show up to it. Okay.
Sure.
All right. I'm going to bring everybody back.
Okay, sounds good.
All right. Bringing everybody back. I hope. There we go. All right, I think that actually worked better than it has in the past, the breakout rooms thing. Anyway, what we're going to do now is I would like you to give me everything that is in a row, you know, plus, plus, minus, whatever it happens to be. So we're looking at the first one now, sodium chloride solid going to sodium chloride aqueous. Just type into the chat or say it out loud what the entropy of the surroundings, system, sorry, let me get that fixed. That's universe. I can't talk and type at the same time, clearly. Universe, system, and surroundings. So universe, system, and surroundings. Type in, you know, plus, plus, minus, whatever it happens to be. There we go. So a lot of people are saying the same thing. So just to go through it, for solid to aqueous, yeah, we've got fixed entities that are in a solid matrix. To turn them into ions and allow them to go free in solution is generally considered to be a positive increase in the system entropy. The entropy of the universe. Does this actually occur? Can I actually produce a 1 mole per liter sodium chloride solution? The answer is absolutely. Yes, I can do that. And in terms of the surroundings, based on these two, it could be a small negative number or it could be positive. Good. Excellent. Excellent. Good. How about the second one? Silver chloride solid going to silver chloride aqueous. Anyone? What would be the values for this second one? Negative, positive, negative. So I got 2 people with responses. Is there anyone else that wants to contribute? All right. So solid to aqueous for the system, you agree with Taylor. Good. You have positive for the system. Again, same thing as sodium chloride. Free ions floating in solution. Should be an increase in the system entropy there. But this does not occur. Sodium chloride is insoluble. It has a KSP. So this process doesn't produce 1 mole per liter solution. So that is negative. And this is either going to be, this just has to be more negative in order for the overall entropy of the universe to be negative. Good. Afrin, go ahead.
Sorry, could you explain to me why a negative universe, because that's what I was having troubles with when I was trying to figure out. Because at first I thought it might have been positive, positive, negative. Because I thought it was the same thing with NaCl.
No, our criteria for whether it produces it, can we form a standard solution? And a standard solution becomes 1 mole per liter, Afrin. So can we make 1 mole per liter sodium chloride? Absolutely, yes we can. Can we make 1 mole per liter silver chloride? No, we cannot. Does that make sense?
And that's because you said it's insoluble?
Oh, it's insoluble, yeah. If you look on the data sheet, silver chloride is the standard chemical that they use when they start talking about solubility. So there's a KSP for silver chloride, and you would have seen it in the examples we did in when we were doing equilibria.
Oh, okay, yeah, thanks.
Okay, not a problem. Are there other questions on this? All right, how about the last one? Anyone? Any people? Multiple peoples? Negative, negative, less positive. Good, right? Going from a free gas to dissolved in aqueous solution, that is definitely a loss in the system entropy. We know that this doesn't occur because we can't produce 1 mole per liter aqueous water. We can put a little bit in, but it's like 10 to the minus 5 mole per liter. And in the context of the surroundings, it could be, as pointed out, little positive, small positive, or negative. Either one of those. Good. That's the general gist. The other question that is on here talks about, again, it's a conceptual question, life. Life is a very complex phenomena. Okay, in order to produce everything from an amoeba to you, you're going to take sugars, carbon dioxide, water to form sugars, and you're going to take individual atoms to form amino acids that are going to produce proteins and DNA, and all of those things have to come together in very organized manner to produce cells, organs, organelles, organs, and ultimately living organisms. So life is very complex. Delta S system for the production of everything from a bacterium to you is negative. Yet you're here. I'm here. Okay, the amoeba are here. How is this possible? Any ideas? And to hint, you have to go back to this. How is life possible? Doesn't the activity of life increase entropy? That's a different story than the creation of life itself. So we're right now looking at how does a organism form in the first place? If delta S system is negative, what must be the case for the entropy of the universe to be positive? Why? Because life happens spontaneously. How does that occur? What must there be of delta S surroundings? It must be more positive. Yeah, the surroundings must be more positive. Where in the environment is the surroundings more positive? Where do we see this huge increase in entropy of the surroundings? Anyone? One location that facilitates life. Not deep sea vents, although deep sea vents creates an environment where life can form as well. You have the sun. Yes, the increase in entropy of the sun through solar processes is sufficient to overcome the very negative delta S system for the creation of life. And so life becomes spontaneous in the environment where there is energy coming from the sun to facilitate the planet supporting life. So the answer was the sun. What I want to talk about here is reversible reactions. We saw them earlier. An equilibrium system is one example of a reversible reaction, but it also needs to maintain a constant temperature. That is, it needs to be isothermal as well. So a reversible reaction when it's at equilibrium and when the system is isothermal with the surroundings. If we have a reversible reaction, we end up with this expression here, and I'm not going to go through and derive it, but it is possible to do that. Delta S system is Q system for a reversible process over T. And I'm going to guess that you don't have the bit of information, well, because the other class said they didn't have it. So the important aspect, I'll come back to this page in just a second, is that when we have a constant pressure system, okay, Q under constant pressure is actually delta H. And that leaves Carnot's theorem to be delta S reversible, is delta H over T when you're at constant pressure. Or rearranged ever so slightly, T is equal to delta H system over delta S system for a system at equilibrium. All right, so if a reaction occurs at constant pressures, we just derived that equation that delta S is delta H over T, and we now have an equation that allows us to calculate the temperature for a system that is at equilibrium. And we'll be using that in just a little bit. Just looking at the time, I do want to go through the next slide just because it ties it all together. What we've done up until this point in time is we've looked at the entropy of the universe, and that is, by the second law of thermodynamics, the spontaneity predictor is delta S universe. However, it is difficult to calculate delta S universe. It is much nicer to have something that depends only on the system. So under certain conditions, we can actually do that. We desire an equation that depends only on the system, and we're going to look at reversible isobaric systems. And I'm not actually going to derive them for you, just going to give them to you as equations. There's two equations here, and both of them are very, very, very valuable. The first one is that we have this parameter called delta G, Gibbs energy, which is on the next slide. Delta G is only dependent on the system enthalpy and the system entropy. The second one links free energy to the entropy of the universe. Delta G is minus T delta S. And that means that since Gibbs free energy is proportional to the universe entropy, it is a spontaneity predictor. So we can calculate delta G, which only depends on the system enthalpy and entropy. And that will tell us whether the reaction is spontaneous under those conditions. And just to finish this off, so if you can give me 2 more minutes, that would be great. What is the Gibbs free energy? It is the maximum work that can be extracted from a system and still have a spontaneous process. We're working at constant temperature and pressure. And the criteria here is that if delta G is less than 0, you have a spontaneous process that sometimes uses the term exergonic in relation to exothermic, similar to exothermic. Delta G is greater than 0, the process is non-spontaneous, and you have an endergonic endothermic process. Exergonic and endergonic are fairly new and really not that widely adopted, so whether they become commonplace, I don't know. But delta G is less than 0 is a spontaneous process. Delta G greater than 0 is a non-spontaneous process. If delta G is equal to 0, you have a system that is at equilibrium. And that's where we're going to end it for today. I'll be here to answer any questions you have. So, I know you have a little bit of writing to do, but if you have any questions, please let me know. But other than that, that's it. Thank you very much for your time and attention. And yes, your exam is on Wednesday, online, same process as last time. And you had an email about it over the weekend. So take care, everybody.